Welcome to the next lecture. Uh, Now today we will do the reconstruction formula of sampling theorem. What does that mean? Yesterday we studied that when we sample g of t, so we represent that by g bar of t. So in frequency domain, g of t we represent by g bar of omega. So g bar of omega is the Fourier transform of g hat of t, and g of omega is the Fourier transform of g of t. G of omega is band limited, right? And g bar of omega is periodic repetition of the same band. And to reconstruct, it means that we need to put an ideal low pass filter like this. Now if you look reconstruction process, is like that we have a filter. To this filter we provide the input g bar of t, and we should get g of t. That is our purpose. So in frequency domain, if we have h of omega as a transfer function of this filter, the input is g bar of omega, then output should be g of omega. So here the frequency domain operation is quite clear, quite obvious, that if h of omega is a rectangular filter like this, then definitely any filter with such response will only allow one spectrum, which is g of omega, and the output will be g of omega. Now what will be this transfer function? Definitely it will be a rectangular function. Okay, it will be a rectangular function, so it has to be here 2 pi b and minus 2 pi b. Okay, and we can write it as ts rectangular omega over 4 pi b. Now there is a reason for writing the ts part here. The reason is, if you look at g bar of omega, that is 1 over ts. Just recall yesterday's formula. N is equal to minus infinity to infinity g of omega minus n omega s. So there are two things we need to be done by this filter. One is to filter out only the this one lobe, and the other is to get rid of 1 over ts. So for that we need to multiply it by ts. So that is why ts stands here. And rectangular omega by 4 pi b means, so you recall the definition of rectangular function is 1 if mod omega divided by 4 pi b is less than half, and it is 0 otherwise. So this means that it is 1 if mod of omega is less than 2 pi b and 0 elsewhere. Okay, so that is what it means. Then ts times rectangle will be ts and ts. Okay, now we have a filter whose frequency domain we represent by h of omega. Let the time domain impulse response be h of t. Okay, so now we need to figure out the time domain relationship. Now first of all, what will be this h of t? You know that h of t and h of omega, they form Fourier transform pair. This you know from basic signals and systems also. So h of t will be Fourier inverse of ts rectangular omega by 4 pi of b. And you know, rectangular function forms the Fourier transform pair with sinc function, and we will directly use that formula here without wasting time. You can look into the Fourier transform chapter of the book on B. Pilati. It will be equal to 2bts sinc 2 pi bt. I again request to those students who are not comfortable with basics of communication system to visit the YouTube channel, and in the playlist of communication system lectures, watch the initial lectures. There I have revised briefly Fourier transform, some of the properties and basic concepts of communication system. Okay. So now this is the filter response, and since I will be considering that we sample exactly at Nyquist rate. So when we sample exactly at Nyquist rate, that means this fs will be exactly 2b, which means 1 over ts will be exactly equal to 2b, that is 2b ts will be equal to 1. When that is the case, then h of t will become simply sinc of 2 pi bt. Now we recall what sampled signal, how we wrote that in the previous lecture. So if you remember that how we wrote the g bar of t was written as summation n g of nts delta of t minus nts, right? And now we are passing this through the filter. So this is getting passed through a filter with response h of t, and then this will be the output. So that will be g of t, definitely, right? Now again, a simple concept from signals and systems. If you pass delta function, delta of t minus suppose kts to the filter h of t, the response will be h of t minus kts. That is why it is called impulse response. Okay. Now if you look at this g bar of t, it is sum of such terms. So for each term of g bar of t, the output will be of this form, h of t minus kts, and the overall response will be then summation g of kts h of t minus kts. Yeah, why? Because here I have shown you the input to the filter delta of t minus kts, but if it is multiplied with this g of nts, the sample value at ts, then this is a constant with respect to the time, so it will be g of nts here. So this will be the overall output, and this will be equal to g of t. Okay, now this is g of the kth sample, and h of t is sinc function, so h of t minus kts will be sinc of 2 pi b t minus kts. Since we are sampling at exactly at Nyquist rate, so so sinc 2 pi bt minus 2 pi k bts. So in this 2 bts will be 1, because we are sampling at 1 over ts is 2b. We are sampling at Nyquist rate. So it will get further simplified as sinc of 2 pi bt minus k pi. So this is called a reconstruction formula. So this shows in time domain how do we reconstruct. It's also called interpolation formula, reconstruction formula, both interpolation formula, which demonstrates that how this reconstruction takes place from samples. How can we reconstruct the g of t? Now this much is about the sampling. There are a lot of things in sampling, aliasing. I will not go into that because our purpose is something else, and this actually should have been done in the BTech level. So now comes the other thing we have done till now. If suppose this is your message signal, what we have done is we have discretized it. We are taking the samples, but the amplitude is still analog. Amplitude can take any value, right? This again is problematic. So earlier the problem was that the signal was defined at every point of time. It was not possible to store. Now you can store it. You have no finite number of samples. Okay, but what value will you store? So the value of this sample can be anything, root 2, it can be e, it can be whatever, 1.11111, any fractional value. So we would like to digitize now. That is the step of digitalization. That's called quantization. What quantization means is, suppose you have this signal. I will draw it like this. The first step which you have done is you have sampled. So I will draw samples with red color. Okay, I will draw these lines also. So we are sampling at Nyquist rate. Practically you should keep rate Nyquist rate more than 2fs. Okay, now the third step is we will divide the amplitude. Suppose I will divide it into 8 parts like this: 1 2 1 2 3 4 5 6 7 and 8. I have divided it into 8 levels, and the rule is like this. You look into, I will now zoom it. So look into any sample. You have to map the value of that sample to the midpoint. Suppose you look into this sample, okay, top sample. Now I will use maybe green pen, this top sample. Okay, so you will not take this value, rather you will take the midpoint value. I am drawing the midpoint value with green color. Similarly, this value you will take the midpoint value, that is this much. Now this also will map to the midpoint, this also will map to the midpoint. Similarly, this value will map to the midpoint, this value will map to the midpoint, this value also, this value to midpoint. Okay, now you will feel that there will be errors also, because as you can see in some cases 2 points are mapped to the same midpoint, right? So we can, what can we do? We can increase the number of levels. Suppose I will draw 8 more, so we have now 16 levels. Okay, so I have increased these levels. Okay, now you can see that earlier this point and this point, they came in the same interval. Now they are in different intervals. So now we will take the midpoint value of this you can say level. Okay, are you getting the point? So any interval, so this and this, suppose, take the midpoint. The sample falls anywhere, but you will take the midpoint value. In that way, we have fixed values an amplitude can take. Suppose if it is 16, so amplitude can take only 16 different values. Is allowed to take only 16 different values. Actually, it will take a lot of values, but we are restricting it to 16 different values. And suppose if you take 8 level case, each level can be assigned. So this process is called quantization. Okay, this process is called quantization till now. Now each level can be assigned a binary code. Okay, suppose I will take the example of 8. 1 2 3 4 5 6 7 8. Suppose this 8, I will give this 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Whenever amplitude falls here, the sample amplitude, we will represent the amplitude binary code 1 1 1. Whenever it follows here, we represent by 1 1 0. Whenever it follows here, 1 0 1. Whenever it follows here, 1 0 0, so on and so forth. So for every sample amplitude, we will get a binary. We can represent a binary number 1 1 1 1 1 0 1 0 1 1 0 0. This coding is called pulse coded modulation. So now, from analog signal, after sampling and quantizing, you now can represent an analog signal with the help of binary codes. Now we have entered into the world of digital world, right? We are into now digital regime. So earlier we had a weird analog signal. Now finally we have ones and zeros. Okay, this is we have assigned a code to each amplitude. Okay, code to each amplitude. Now we need to represent these binary numbers by some waveform. So we usually represent, suppose, 1 by plus signal, some plus a, and 0 by minus a. This is called a non-return to 0. Non-return to 0. Okay, and this coding, that to represent a binary number with any waveform with any pulses, this is called a line coding. Okay, line code. We can also represent binary 1 by plus a and 0 by nothing, no signal at all. This is called return to 0. Okay, so there are several others. We will mainly restrict to no return to 0. This has much better properties than return to 0. So what we have, so you had a analog signal. You did sampling. Now you had a sampled signal. You did quantization. Then you did pulse coded modulation. Now you have binary ones and zeros. Now you do line coding. Now after line coding, you exactly have a signal which is a binary digital signal, which is of this type: 1 and 0. 1 and 0 represent the plus a level and minus a level. Is it? So I think the process is now pretty much clear. Now our next target will be how to transmit those binary digital pulses or signals over a channel. And in the presence of noise, what will be the performance? That is, what will be the error rate? Definitely, what error can happen is 1 can be changed to 0, 0 can be changed to 1. There is one more error which I will see, that I may post separate video for that. That is called quantization error. As you can see, the amplitude level falls anywhere, but you are always mapping it to midpoint, so there is an error, right? So that error also can be quantified. Definitely, to decrease that error, you need to increase the number of levels. So there's a trade-off. If you increase number of levels, you need more and more number of bits. Suppose now 16 levels. How many bits you need? You will need 4 bits to represent each level, right? For 8 levels, you needed 3 bits. So you can increase number of levels, but there will be more and more storage needed. Complexity of the system definitely will increase. So these trade-offs we will have to go through, and we have to see what is our need. Suppose if you have a satellite communication, then in satellite we can tolerate any level of complexity. So you will see in satellites we can have lot of levels. Even on CD, when you store the data in digital form on CD, we use this pulse code modulation there. We can have even 1, 0 to 4 levels also, very large number of levels. But now suppose when you are communicating using your mobiles, and that to audio signals, you don't need lot of levels, because audio signals have a lot of redundancy. If you remove a lot of bits, we don't, there is no problem in recognizing the voice. So it depends upon how much accuracy you want, what is the system, how much complexity you can afford. That we will see now in subsequent lectures, what is the performance of these binary signals in presence of the noise.